David, are you there? Can we bring you back on the screen? Okay, no problem. Oh, brilliant. Okay, so Jeremy's just going to do a quick intro. All right. Okay, over to you, Jeremy.
Hello. Is that working on the microphone? Just about to.
Yeah, you turn it on? Oh, it's a mattress.
Hello. That's all right. That sounds better. Okay. So thank you very much for coming. A warm welcome to the final event of Muswell Hill Sustainability Group Green Open Homes 2025. This is the third talk. The other two, if you missed them, you can watch them again on YouTube. The same will be true of this talk as well. And also a warm welcome to all of those who are watching us this evening on the live stream. So we have three speakers, and the plan is for us to hear from each of the three speakers in turn. And if you have questions, we'll then have a panel where there'll be some time for any or all of the speakers to address your questions at the end. And we have our first speaker is not with us in person, but is with us live on the screen. David Farmer, who is a research fellow at the University of Salford, which has the Energy House Laboratory, which is what he's going to talk about. And then I'll introduce briefly the next two speakers when we get to them. So, David, thank you very much indeed. Very much appreciated that you've taken the time, and I'll hand over to you.
Involving air source heat pumps and their installation in solid wall hard to treat homes. A little bit about Energy House 1. 1 second. So yeah, it's a replica of a pre-1920s Victorian end terrace. This is actually built with reclaimed bricks from a house in Salford that was being demolished, built to traditional kind of practices. This is an end terrace with a neighbour, got solid walls, it's got suspended timber floors, lath and plaster ceiling, so pretty much representative of around about 20% of the UK's hard to treat housing stock. Why do we call these houses hard to treat? That's mainly because of their wall construction. So there isn't a cavity in most houses built before the Second World War, especially anything before 1919. Very rarely they've got a cavity in there, so it's difficult to put cavity wall insulation in, so they're very difficult to insulate. So typical performance of that kind of house. And we've filled it full of sensors, monitoring temperature, environmental conditions, hundreds of sensors in there. And we're able as well to automate occupant usage of energy, so we can automate windows and doors opening, we can automate domestic people using hot water, appliance use, even metabolic gains in there. So the most important thing about the house, which sets it apart from pretty much any other, is that it's in an environmental chamber. So in that chamber we can replicate external conditions, so primarily temperature, but we can also introduce rain, wind, and the effect of solar radiation on the building as well. And that provides us with a repeatable test environment, so we can measure the impact of changes to its heating system or to its building fabric in terms of insulation measures more quickly and more accurately than we can do in the field. So especially very small kind of changes in energy use, which you might not be able to measure on an individual house because of the weather might have impacts or people's behaviour. A few bits of jargon before I steam in. Some of these some of you may be familiar with, but they're pretty much in terms of the air source heat pump world. The spark gap is a massive issue at the moment, so that's the electricity gas cost ratio. Currently, electricity is 4 times more expensive than gas per kilowatt hour. So that's obviously having implications in terms of the affordability of electric heating systems for decarbonisation. Coefficient, a COP, or coefficient of performance, is a measure of air source heat pump efficiency. So basically, if you have a COP of 3 for every 3 kilowatts of heat coming out of the air source heat pump, you're only having to put 1 kilowatt of electricity into it. So unlike a gas boiler where you can't really get can't really get 100% efficient near enough with a gas boiler, that's a ceiling. Heat pumps can be more than 100% efficient. Obviously a COP of 3 means that if you're putting 1 kilowatt of electricity and getting 3 out, with a spark gap of 4 at the moment, if you're switching from gas to electricity, there's a good chance you're going to be spending more money in terms of your heating. And the COP is just efficiency under a certain set of conditions. So when I'll be giving some COPs today, they're measured on what we call a typical winter day. So it doesn't apply to the whole heating season. So it's efficiency over the whole year, something called a SCOP or an SPF, seasonal performance factor. So a little bit of background really in terms of heat pump end use. Department for Energy Security Net Zero did a project looking at heat pumps in the real world, and we took some of their data from houses that are like the Energy House, so houses before 1945, so probably hard to treat, and looked at the performance of those heat pumps from that sample. And as you can see, the best, I don't know whether you can see the text, but the 3 smaller bars on the chart there are the best, medium and worst performing heat pumps, and they are all use significantly less energy than an A-rated gas boiler, well, any gas boiler really, in terms of heating the house over an entire year. So obviously if you're getting that electricity from green sources, renewable sources, great for decarbonisation. However, if we go back to the spark gap issue that we discussed a moment or two ago, we can see that on the left hand side, the best performing heat pump here was cheaper than a 90% gas boiler if you include the standing charge for a gas boiler, 90% efficient. But the median performing heat pump there, more expensive than an A-rated gas boiler. And the worst thing really is that the worst performing heat pump in this sample would cost in effect more to heat the house over a year than an E-rated gas boiler that was put in the 1990s. So a couple of things stand out here really. It's quite easy to mess a heat pump up, and in fact there's more variability in the performance than you might see with a gas boiler. So we wanted to really do a couple of tests really looking at these things in more detail. It doesn't really have these houses, we don't know a lot about the heat pumps, and we don't really know what the cost of the gas was. So these are all modelled energy costs. So we did some work with National Energy Action, which I think is applicable to solid wall homes and period homes in terms of looking at an air source heat pump. And we were looking at air source heat pumps that have been installed under the Eco4 scheme. So that's funding for fuel poor households. We just measured what would be called what would be a best practice typical air source heat pump going into the energy house. And the energy house, when we were doing the test, had no insulation on the walls. It had a 270mm loft insulation, so that's maybe what a lot of people might have had under some funding, and some E-rated double glazing doors. So that maybe doors that were installed in the 1990s or 2000s. So pretty much a typical house, one of the typical hard to treat home. And we were then measuring the air source heat pump performance and gas boiler performance in winter on a winter day, and look at the costs in that, and comparing air source heat pump with the gas boiler. And when we put that heat pump in, yes, it was we overheat the house a little bit, and to have similar heating with the gas boiler, that it said it'd be like 17% more expensive and 28% more expensive than the gas in terms of the temperatures that we were wanting to get from the heat pump. So some of that, people sometimes install heat pumps without radiator valves. They say that's good practice, but it can lead in those homes are obviously going to face an increase in fuel bills. So we looked at what we could do to improve the performance there. And so we optimized the heat pump. And if you see the two charts here, went from the coefficient of performance 3.2 to 3.6, and we reduced the energy use and obviously the cost, because it's electric, by 22%. And that had obviously we also as well improved the internal temperature control. And to do that, we had to make a few modifications, and we also did lots of measurements on the house, and we were able then to put the right size heat pump in and put the right temperature flow through the radiators, so it kind of improved the performance there. And the thing about with air source heat pumps as well, when we look at them, and we've got it might be quite hard to make out some of the text here, but the blue portion of these charts here in the bedroom, these are giving a proportion of time spent in the bedrooms overnight. And you can see the gas boiler that most of the overnight temperatures in the bedrooms, people are spending those in conditions below 16 degrees, which is considered unacceptably cold, for health reasons during sleeping. People tend to like to be between 16 and 20 at the top end, really. And the temperatures really were dipping, like in the bedroom too, which would be a child's bedroom, down to about 13 degrees on a night. So that's using a heating pattern which a gas boilers typically people will do, in terms of having the heating on in the morning and heating on again in the evening. So this is the evening heating period here. So actually what we were finding, yes, even though the air source heat pump was a little bit more expensive, well, we've actually got much healthier in terms of internal environments for people living in there, less risk of surface condensation, mold growth in some issues, in some circumstances. So we were able to stop some of the overheating as well with these modifications we made to the system. And basically, after we'd done all those tests, we were able to then have the air source heat pump running at the same cost as a gas boiler on a winter day. But we also had a look at using a different heat pump tariff, an OVO, do a tariff for 15p a kilowatt hour. And if you'd use that tariff with the heat pump, you could be up to almost half the price of a heating house with a gas boiler, with all that improvement in and healthier internal environment. So certainly these heat pump tariffs are essential really for people maybe with hard to treat homes in terms of going over to an air source heat pump. The one problem we have though is we were testing a Samsung heat pump, and that wasn't basically you couldn't use that OVO tariff with the Samsung heat pump. So a bit of recommendation there really is to check out and make sure you get the right heat pump tariff for your heat. You can get a heat pump tariff, smart heat pump tariff for your heat pump. We also, as well, to have similar heating costs as well, we had to remove the standing charge, get rid of the gas meter. That could have some associated costs with potentially having to change your cooking appliances, any rewiring that might entail as well. It's worth noting as well that these are costs on a winter day. Air source heat pumps in maybe the shoulder seasons, in spring, in autumn, they'll be more efficient. Their costs will be higher, and so actually over the rest of the year, you know, it could work out that it's significantly cheaper than a gas boiler when we've done these measures. So really, that's with a hard to treat house, but obviously there's things you can do in terms of making that house more energy efficient before you put a heat pump in, and potentially then help in terms of looking at the running costs of a heat pump. So we did a project with Desnes called Deep. You can find all the details of that on the web. But in effect, what we did was we performed a stage retrofit of the energy house. So we started off with it in a pretty much uninsulated state. We had 100 mil of loft insulation in there, an E-rated glazing, and then we went through and insulated each element in turn, going from the cheapest to the most expensive. And at selected stages that we were testing the air source heat pump and the boiler to see at what stage during that fabric retrofit journey that the heat pump and the gas boiler costs were comparable or cheaper. And again, with these tests, we just done simulating a typical winter day. What we can see from this graph on the right is these red bars represent the reduction in the heat transfer coefficient. I don't think many of you have heard of that, but effectively it's the fabric energy efficiency of your house. And sooner or later, a lot of you will be starting to get understand the heat transfer coefficient of your house, because there's technologies becoming available now through smart meters and in-home displays, which can provide you that energy efficiency metric of your house. Not as accurately that we can measure it, but in effect it tells you how energy efficient your house is. And these red bars here are the percentage reductions in fabric heat loss resulting from each retrofit measure. And so with the roof, we started off with a 1% reduction. So we'd already had some insulation there, topping it up didn't really do much. But you can see the big one here really is, and the ground openings and the ground floor, we'd by this stage had reduced the heat loss by 10%. But the big one's the external wall insulation. The problem with that is that external wall insulation is very expensive. Our costs here for the retrofit, I wouldn't pay too much attention to those because we're a university, we always get ripped off. But in essence, the scale is it kind of gives you an impact in terms of the relative costs of these measures. These whole house approach measures here were where we were doing best practice details after the piecemeal retrofit, looking at trying to reduce the risk of surface condensation and mold growth at junctions, which we pretty much eliminated, but that upped the cost of the retrofit from £20,000 to £30,000. So, and with no real extra energy saving to go with that. So that does ask a question about who's going to pay for these measures in terms of creating a healthier home, because they might not pay themselves back in energy bills. Well, obviously, in this test, this was before we did the NEA tests, we wanted to see, is it possible to put the heat pump in before you spend all that money on some solid wall insulation, because it's a big cost. Obviously, the impact of this whole retrofit there, in effect would reduce the heat loss of the house by half, so that should halve the heating energy bills, the space heating energy bills that are required to keep that house warm. So if we go back to these coefficient performance, we started off with the roof and the openings retrofitted, and we had a COP of 3.1. Then we retrofitted the floor, and it stayed at 3.1. And then we put external wall insulation on, and we have a lower flow temperature through the radiators at that point because we're losing less heat through from the house. And because of that, we should have seen a big increase in the COP of the heat pump. But we didn't. It went down, and we found out the installer had connected the flow and return pipe work up back to front on the unit. That might sound a bit crazy, but it's not the only time it's happened at Energy House, so you've got to wonder what's going on in the real world. but the heat pump was providing the same sort of space heating as other stages. We were able to tell this pretty quickly because we got a research facility, so it told us what was going on, but people in the real world might not find out in terms of what the cost of, you know, a poor installation. The heat pump wasn't telling us that. Unfortunately, we didn't have time to go back and rectify it because it was a small part of that project. But if we based it on the COP of other stages, we would have found that when we did our analysis in March 2023, that the gas and electric would have been the same price, but we suspect air source heat pump would have probably been cheaper if we'd been able to get a proper measurement from it, if it had been correctly installed. But we're going back to spark gap again, because if the heat pump had been put in February 2021, the air source heat pump would have cost more than the gas boiler at the final stage, this retrofit stage. So the 2 stages before, the air source heat pump's more expensive, the red bars. So really it's kind of telling us that in some instances we might actually need to put solid wall in the house to kind of get these costs comparable. And the spark gap is not just in terms of what's happening now in terms of spark gap when you decide to invest in an air source heat pump, but it's actually getting wider at the moment. So the problem is that it had narrowed at this stage here, but now it's getting wider again. So you've got financial decisions. You've got to be really quite careful in terms of looking at the economics, and I think it's up to the government really to do something in terms of narrowing that cost between gas and electric. Also, quite interesting to see the energy costs are far greater of 2 years. You know, in the gap of those 2 years, from like around about £1 a day up to £2, or double the cost for a winter day. So yeah, we've got some. So the base of all this, it's got some recommendations for hard to treat homes. So these don't just apply to homes in fuel poverty. These will be for any solid wall house. I would. I don't want to sound like that I'm being putting a downer on air source heat pumps. I live in an uninsulated solid wall house. Well, my walls are uninsulated. I'm a tight Yorkshireman and I have an air source heat pump, so you can get them to work. I think it's just very important in terms of finding the right people to design and install them. I had someone come and drive 200 miles to put mine in, but you know, I'm sure there's some good people down in London. You don't have to get them to drive down to find you. But in terms of recommendations, we'd certainly recommend making sure it's compatible with the tariff. The only problem maybe with the tariff is that it can be withdrawn as well. So home batteries and air source and using off-peak energy to charge your battery and then run your heat pump seems like a big win. But again, there's a cost in terms of the battery installation. We've also tested some hybrid heat pumps where you retain your gas boiler, and that can be used for providing hot water, domestic hot water. So that's really quite useful in small homes, maybe like the energy house, where cylinder cupboards may have been removed. People might have used that space for storage where it's limited, or got an ensuite. So you can get hybrid heat pumps which use a gas boiler, and they can decide when it's cheaper to heat the house with gas or with the air source heat pump. So again, they might actually be useful in some circumstances. We designed our heat pump, if we can do it. We try and do some measurements before we design, put our heat pump in. So maybe if you can just measure the air tightness of your house before you do that, that gives you a good idea maybe of what the ventilation rate is, and that'll help you get the right size heat pump for what you need, and maybe hopefully more efficient. Obviously there's solid wall insulation, but you know it is expensive, and I think we're seeing a lot of the headlines out there. It's not risk free. But it does have the benefit as well of reducing the heating that you need and providing that internal quality in terms of more healthier internal environment. Again, I've mentioned it already, but it's the quality of the system design and the installation which is paramount, getting that right in terms of being able to ensure that they work properly. And just a few little easy wins for you guys based on stuff we've done at the Energy House. Reducing your boiler flow temperature is a good one. We did some work with NEA, which formed Nesta, which formed the basis of the government's campaign to reduce your boiler flow temperature. there is a one size fits all. They recommend 60 degrees, but in a cold snap, you might need to go warmer than that. You might have to have a warmer flow temperature than that because houses might not heat up and up. So it's you might not be able to heat the house up and up in a cold snap. But if you're going around someone's house and they don't know, make sure you tell them how to, and you do that for maybe a family member or a friend, make sure you tell them how to switch it back up again if it does get too cold and they can't maintain it. I did it with my girlfriend, so she went mental with me because it got too cold. Luckily no one's hurt in that instance, but just be careful about it. But some boilers may already have that inbuilt in terms of weather compensation. Heating controls, that is the main thing in terms of getting a heating system working correctly. One of the main things is making sure that it's actually properly controlled. So if you can get certain modulating controls to your boiler, they'll improve its efficiency. Making sure you've got thermostatic radiator valves on your radiators. So apps as well, that maybe if you've sort of left your heating on when you go out, if you can switch your heating off, that'd be great. We tested some reflective radiator backing at Energy House, and we found that it reduced the gas use on a winter day by 3%. Now, that was for Energy House is a solid wall house, so if you've got radiators on external solid walls, that helps reduce the heat flow. Then you don't necessarily need to buy a product like that. You could probably use a bit of tin foil just to actually reflect the heat back from the wall. But these ones actually had it on the radiator, which is lowering the heat, lowering the emissivity. It's a bit, I won't go into that actually. But look into reflective products. Thermal curtains and blinds. Again, it's a law of diminishing returns, but if you've got some single glazed windows, we tested a blind that in effect reduced the heat loss. Well, there's 5 times less heat flow through the heat loss through the window with the blind closed. So obviously you could use like secondary glazing, but also blinds and curtains as well can do some pretty good. And draft proofing is a big one, but just make sure you're keeping the ventilation in your house. You're not blocking up anything that's providing ventilation to maybe under your floor or required for appliances. And the big one, pretty much whenever I've gone out testing houses in the real world, is the perimeter of a suspended timber floor. So that's normally a big one in terms of drafts. All right, thanks very much.
Thank you very much. Fantastic talk. Really appreciate it. Thank you. So I'm going to go straight to introduce Dermot Barnes, who has heroically come despite being injured, and who has been very central right from the start with Muswell Hill Sustainability Group and also with Energy. So he's been right at the heart of both of those organisations from the beginning. And so I will hand over.
Thank you, Jeremy. Sorry, apologies, try again.
How's that? Oh, yeah, great, we're there. Great, thank you for the introduction, Jeremy, and thanks, David, to the most scientific input we have for this evening. I'd like to just, first of all, introduce myself. I'm going to talk about. So I currently work as a Director of Sustainability at a university in central London. And I have responsibility for net zero and a whole range of different things, including education and research programs at the university. Everything essentially from A to Z in sustainability. But in former lives, and that's the bit that's interesting and valuable for you, I guess, I've been involved in the design and delivery of more than 600 retrofit projects from single interventions in sort of single-family dwellings right through to multiple kind of social housing units for councils. I've worked on both the client side and the consultant side, and also as a contractor. So I have a pretty wide range of experience in the sector. Probably been at it for too long, but in any case, you'll get some interesting and practical observations this evening. A couple of things I'd just like to caveat. This is a complex subject. There's an awful lot of detail to absorb, and there is no way that the kind of brief amount of time we have this evening will do justice to everything you would need to know. But hopefully, between Stewart and David, we'll arm you with a good introduction to the principles and procedures, and hopefully help you to make some better informed decisions about your own retrofit projects. Perhaps one other thing to mention to you is that this evening I may make reference to particular materials or systems. That is really just for convenience of reference and ease of illustration. As the lawyers are inclined to tell you, there are other products available, other systems, other manufacturers. So I'll sort of jump into the detail, hopefully getting this to go in the right direction as opposed to the wrong direction. Let me do that. Say again? Sorry? Try again now. Okay. Not so far. Hang on. Ah, there we go. Great. Thank you. Okay, hang on. Sorry. Pressing all the wrong buttons here. Sorry.
Okay, maybe the cable's come loose. Okay, I'll go and sort it.
Shall I just ask you to move them on for me?
Yep.
Okay, great. Thank you. So before we jump into the detail, I'm going to just ask you a quick question, a kind of a straw poll. I guess you're all here because you're interested in doing some retrofit measures to your homes. That's kind of taken for granted. But can I just ask, there are probably 3, maybe more, reasons why people are interested in doing this. The first is, maybe trying to decrease your energy bills and saving some money. The second is that you might be interested in doing something for the environment, for the planet, and maybe the third is that you want to just simply be more comfortable in your homes. Now, probably everybody here wants to do a little bit of all of those things, but can I ask you to just prioritize and tell me with a show of hands, which is your primary motive in all of this? Number one, how many people are interested in the sort of energy savings and the money? That's the primary driver. Okay, that's really interesting. So far 2 people are confessing to that driver. The second one is obviously the whole business of the environment and the planet. Who is driven by that more than anything else? Okay, really interesting. Okay, great. And then the last one is the whole comfortable business. You don't want to be chilly and miserable in your home. Okay, fantastic. It's a really interesting show of hands, and it's a selfish motive for me to just understand what drives people when this happens, and when people take those steps. If you could move us on one, David, thank you.
Did you just try once more?
Yeah, let me try one more.
Okay, I'll do it from the center.
Okay, great. Maybe actually if you just go straight on to the next one. And one more. Great. So this is just to contextualize this. This is several years old now, 2021. There's probably been an update that I haven't downloaded. But these are the reallocated energy sector emissions. So it's just important to understand when we think about this. This evening is all about the sharp end of the shovel, so to speak. But while we're talking about this, we do have the sort of issues going on in COP 30 in Brazil at the moment, the other end of the shovel. But when we just think about this, it's worth remembering that our homes account for around about 30% of the energy that we're using in the UK. So the whole net zero journey is one that makes tackling our homes imperative. We are absolutely not going to get to a place where we will be living in an acceptable temperature, climate change wise, unless and until we deal with this comprehensively. If you could move us on one, please. And again, thank you. So what that actually means for the UK is about 25 million comprehensive retrofits. That means deep retrofits need to be carried out within the next 30 years, essentially to every home that was built before 1990. And I would, also throw into the mix the fact that we're still building at appallingly poor standards, and the houses that are being built today are not fit for the changing climate and the 2050 net zero vision. So the government still allows us to perpetuate a situation where we will have to retrofit the new build, the so-called highest quality buildings that we are building at the moment. And just, if you could move us on one more, thank you. And just to put that into, silly context, it's 833,000 homes per year, or one every 40 seconds. So, needless to say, we're a bit of a distance away from that at the moment. And this is, scientific advice from the government's Climate Change Committee that tell us that this is what we need to do if we're going to hit net zero. So we all have a role to play in that. If you could move us on one more, David, thank you. And really, what does it mean? It means that right now, we're doing things at about a fifth of the speed that we should be doing them at. So 5 times faster is what we need to be doing things at. And that's to have half a chance of staying within the 2 degrees warming that the IPCC have told us is imperative. And that factor of 5 is not my hearsay, it is scientific context. So if you move us on again, please, David. One more, please. Okay, so I'm going to speak now about the guiding principles of a successful retrofit. Oh, okay, fantastic.
So this way to go for.
Oh, brilliant, thank you very much. Great. So I'm just going to talk about 4 key principles, which would really be the 4 most important things to take away today. When you're designing and considering retrofit, start with the fabric. That's the first principle to think about. The fabric means the building fabric, not the energy systems that heat or cool or power the space. Secondly, use a whole house approach. Do not think in isolated pieces. That doesn't mean you can't do things step by step in a programmatized way. It just means you have to consider the implications of measures if you're going to do them one at a time. The third one is do not insulate without ventilating. When you make your home more airtight, as does happen with insulation, and it is different, I should just mention that airtightness and energy efficiency, airtightness is one important part of energy efficiency, but insulation systems generally start to make a home warmer and change the way the home breathes. So it is necessary to balance that with ventilation. And the last point, which is these key guiding principles, is that if you are going with any kind of internal wall or external wall insulation system, or indeed any insulants at all, I would very strongly recommend you use a breathable, vapor-open construction approach. Now, I can't go into the detail of what that means, but it essentially means that your building continues to transpire. The moisture that is built up on the inside of the building transpires to the outside through an intelligently designed system, rather than one that retains moisture in the building. So if you get it right, or if one gets it right, I don't mean you personally, one gets it right, you will have good design plus good construction, which includes monitoring and evaluation, delivering reduced fuel use, reduced costs, reduced CO2 emissions, and improved comfort and health. And by the way, it will also increase rather than necessarily decrease your asset value, your home. And these are all absolutely essential considerations, especially if you have, as most of us do, solid wall buildings. I'll move on now to the sort of approaches. I've just spoken about the principles and what that might deliver for you. Now, I'm going to apologize. This is a fussy diagram. It actually started life as a much more complex diagram, and this is a simplified version, believe it or not. So I'm going to try and start us in the the top right-hand corner, the bit that talks about building regulations, this bit here. So these are the baseline considerations in any retrofit. These are the regulatory mechanisms which influence how you carry out construction work. They tend to pertain to things like ventilation, to construction, to structure, to fire risks, to all sorts of other things, and they are the things that your building regulations inspector will want to see satisfied. They are woefully inadequate in relation to what we should and could be doing and need to be doing to meet net zero and make energy efficient homes work properly. They're so far behind as to be almost beyond a joke. So as you make your way, and I should say, you may also be regulated by planning legislation. So Town and Country Planning Act may also have certain construction requirements that will affect your project. As you move down here, and as you move around this, you'll see, first of all, everything is related, okay? Now, they're related insofar as you start here with your baseline, then you have other systems that you can consider, including the passive house system and various other initiatives which try to take this baseline and make it fit for purpose for the 21st century, to make a home work the way it should work in response to the climate and the energy crises that we have been facing. Now, I won't go into all the details of all of these. There are different systems that can be considered in different ways according to your project and your budgets and everything else. But what I want to just focus on most is the past 2035 methodology. So several years ago, the government launched this PAS 2035, which is publicly available standard 2035, which was in response to a series of systemic failures in the marketplace, the deregulated marketplace around the insulation and retrofitting of homes. So you will have seen various headlines at various points in time about, and these have continued, about national insulation programs that went wrong and caused mold growth and problems in people's homes. So the past 2035 standard was designed to try and remove some of that risk. And what it does is it uses a series of principles or cornerstones, 3 of them. It starts with what's called a dwelling assessment, which looks at the energy efficiency of the building as it is at the moment, the floor plan, the condition of the building, and the occupancy assessment. Those form key ingredients to the design of a retrofit. It then develops what's called a medium-term intervention plan, MTIP, or improvement plan, which looks at what you might be doing in response to other works you're doing in your home and how you might time those to be maximally cost-effective. And what it also does is it uses an improvement option evaluation. I'll show you an example of one of those in a moment. And what the system does, the way it works, is that it essentially ascribes responsibilities to 3 key people. You have a retrofit designer, a retrofit assessor, and a retrofit coordinator. And those people all take responsibility for designing a successful series of interventions that minimize the risk of unintended consequences. So very quickly, kind of galloping through, it starts with a risk assessment, as I said. It then has a whole dwelling assessment, a retrofit design, an installation program, testing and commissioning, monitoring and evaluation, and eventual project registration. Now, the project registration bit is interesting because we think, well, why do we want to have this registered? So we go back to, most people's primary asset is their home. You do not want work carried out to your home which puts it at risk and makes it unsaleable in the future when somebody comes along to buy your home. So if you've done an extensive retrofit to your home, you ideally want to be able to certify that the work that's been carried out has been carried out to a standard that guarantees its safety and security. So there's a national register available now for buildings that are being retrofitted, and you can then reference that when you come to sell or indeed to rent your home. So that's the sort of final element in that equation, that project registration. So before I just move on to the elements of this PASS 2035 methodology, I've spoken 2 or 3 times about risk minimization. Does anybody have any suggestions as to why there would be a risk, what those risks might look like? Why do we need a risk minimization or assessment methodology? Does anybody have any thoughts on what that might be and why that might, why it might be important?
Examples of poorly installed insulation, spray foam. So let's repeat things back, because otherwise it won't be heard.
Yep.
If you repeat things back, otherwise it won't be heard on the audio.
Sorry, I need to repeat them back. Okay, so apologies. Yes, so one of the audience members has mentioned the risk that comes with spray foam. Spray foam insulation has been a method, a cheap and nasty method, which continues to be advertised, for example, for the treatment of roof spaces and loft insulation. And that has led to mold growth and decomposition of roof timbers and basic structural flaws in buildings. So that's just one example of a whole wide range of things that can and do and have gone wrong from ill-considered retrofit design. So I'll move us on in the interest of time. So let me just go on to the next bit. So this is why. This is an example or a list of the reasons why you would want to think about this. So you don't want your building to underperform. You spend a lot of money on it. You want it to do what it's supposed to do and save you some money. You want to help the planet and you want to be more comfortable. These things can all go wrong if you don't design your retrofit the right way. You also have perhaps a bigger risk, which is around indoor air quality. The kinds of products that often are used produce or can often off-gas, which basically introduces a risk to air quality, and it can also reduce the quantity of fresh air in the space needed for habitation. So there's and condensation and mold growth and all the rest of it that goes with it. And there is a phenomenon. It's not really a phenomenon, but a thing called sick building syndrome, which has been diagnosed as a problem that results from poor design in building retrofit. So if I just move on to the next one, how? So this again is just to revise the fact that there are several different approaches. Fundamentally, you have risk profiles and design paths. It's worth mentioning that every period building, i.e. any building older than 1919, is defined as a high-risk building and needs to follow, with the PASS 2035, a high-risk methodology. And then you have medium and low risk, and that depends on the building typology. Then you have these responsibilities that I spoke about in the previous drawing and the previous graphic, where you've got the designer, the assessor, and the coordinator. And it starts with an assessment of the existing condition, occupant patterns. So for example, anybody who comes along and retrofits your building without looking at the status of the building and checking that things are the way they should be, is not doing you a favor. They're doing something without considering what might be wrong and what might be negatively impacted by what they're going to do. You ideally need to fix problems in your building first. So if you have leaking gutters, for example, water getting into your building, you have moisture rising through your damp-proof course through the ground, you have to fix all those things before you start doing other things that could be made worse by what you then do. And then what it does is it recommends demand reduction, energy efficiency measures, and residual energy strategies. So let me just move along. And this is what it aims to do. The methodology is, helping and supporting a sequenced single or multi-phase intervention at a bespoke program to each property, looking at your particular needs, your particular aspirations, and of course the way you want to use your building now and in the future. And it is underpinned by, as I said earlier, a fabric first approach. And it provides this registered record for future buyers. And when you get your report, if you're doing one of these, you'll wind up with something that looks a little bit like this. This is one page, which is the kind of optimization of the various different measures you can take. It'll give you some sort of indication of what the capital costs are, what the carbon cost effectiveness are. It also ranks the disruption factor in terms of how much hassle and difficulty you'll have to go through. And there are other aspects. This is just an example of one page of one typical report that is used to help to communicate what you should do. Okay, I'm going to gallop on again. So just looking at the elements, when you're considering your retrofit, this is a quick run through of the things that you're likely to need to consider in any retrofit program. It starts with a fundamental consideration that around about 20%, something between 15 and 20, is the stuff that is not quite so important. The stuff that really matters is space heating, hot water, and to an increasing degree, cooling in buildings. So if you then just quickly look at this, and it'd be really interesting to see what David's findings are in terms of the energy house in Salford. He talked about heat transfer coefficients, HTCs, which essentially look at how fast heat leaves your building. Once you you heat the building, how fast does the heat escape? And it'll escape through all these different elements. And again, David was talking about the 33%, or that the amount of heat that gets lost through the walls, and why external wall insulation or internal wall insulation is a primary consideration. But you'll see also that around about 25% will go through the roof, 20% or 22% around about that, and doors and windows, floors, and ventilation and drafts will account for about another 15 to 20%. And this is a typical example. It's not necessarily your home. Every home will be different. Sorry, there we go. So I'm going to start with the lofts, just to give you an idea. This is a super quick whiz through. So on the left-hand side, you see a kind of a typical loft where you're just insulating at the raft, the joist level, so the ceiling joists below, and you'll see different approaches here. You'll see that this is sheep's wool, as it happens, that is laid in between the joists and then on top of the joists. In this case, it was about 300 mil. But what you'll also see here is a rigid insulation solution, which allows for you to use some storage. But when you're doing work at a pitched roof level, you really have to be careful what you're doing, mainly to not block ventilation. So you'll see here, for example, there is a space on the cold side of the insulation to allow air to travel from the ridge to the eaves in this pitched roof. Solid wall insulation, so I'll run through these very, very quickly. So on the left-hand side, you've got external wall insulation. This is a wood fiber project, 2 wood fiber projects that I did, 15, 20 years ago. These are internal wall insulation projects again. These are local projects that were done in Muswell Hill, using breathable wood fiber and natural insulation systems throughout. Render was lime-based render to allow the moisture to pass through the fabric. Here you'll see another approach which has often been taken. It's internal wall insulation, vapor closed. So essentially you create a sweated environment, essentially a plastic bag with insulation on the other side of it, and you rely upon controlled ventilation to allow all the moisture to pass from the inside to the outside. If there's any failure in that, that's what happens. Mold growth. So I would very strongly advocate you completely forget that methodology and you think about these methodologies, internal or external. Floors, very quickly. Stewart will talk about this in a little bit more detail later, as that's his speciality, but there are numerous approaches. The ideal one is one whereby you are dealing with 2 things. First of all, the heat transfer, so you're insulating, but you're also using an air tightness membrane to seal the perimeter and the top so that there is no air gaps. So you're doing 2 different things. And you'll see here, these are different membranes that are being used, air tightness membranes around the perimeter of the wall. So just jumping on, this last slide in this section is simply about the ventilation approaches. So in this sort of funny 3D kind of drawing, you'll see all the different places where air gets in. and where heat is lost. Roughly speaking, windows and windows surrounds, about 18 to 20%. Permanent ventilation, that is supposed to be controlled ventilation, is about 10%, and the rest of it, about 75%, is through all these other things, loft hatches and all the different other places around a building. So, these buildings that we live in mostly were not built to be airtight. They're exact opposite of it. And what you need to be doing is looking at airtightness membranes that go around the perimeter of different junctions and piercings in roofs and walls, tightness around windows, etc. And the important thing I spoke about earlier was the whole idea of ventilation. So there are some golden rules that are set here around the fact that this is part F of the building regulations, and it specifies that you should be having in the region of 30 litres per second per person, or 50 litres if there are smokers in the home. So there are various ways of doing that, lots of different equipment out there and options available for doing that. But it's increasingly necessary. The more insulation and airtightness you introduce, the more ventilation you have to allow your building to experience. So we're getting close to the end, you'll be glad to hear. When we talk about all those fabric first approaches that we've talked about and we've introduced, you're then left with what do you do next? How do you deal with the residual demand? And typically you're doing that by getting off of gas and getting onto electricity. And we've had lots of talks earlier about the whole idea of air source heat pumps and the coefficient of performance that David mentioned earlier. You put in 1 kilowatt hour of gas, you get out about 0.9, so you're losing something like 70 watts. So this is an important thing to understand. Even the most efficient gas boilers will only be about 91 or 92% efficient. Whereas if you get it right, and there's a big if, as David's presentation explained, if you get it right, you can get somewhere between 2.8 and 3, even more if you really get it right. So I have some very high-level principles to suggest to anybody who's considering an air source heat pump. These are my kind of gut feel golden rules that some experience has taught me over the years, and they're not a million miles away, I think, from what some of the principles David was talking about earlier. So the spark gap, you'll now be super clear on what that is. 3 to 4 times is the price gap between gas and electricity. So you need to get it right, and I'm suggesting there's one of two, ideally 2, things you should be considering doing. You start by reducing the demand in your house through the fabric measures, etc., by around about 60%. That should be the aim. Or you should have a solar PV array. And you could, exactly as David mentioned earlier, consider the solar PV array in combination with a battery and get the timing right. And I'm very grateful to David's points about getting the tariffs right when you have an air source heat pump as well. That's not something that I've had any experience of so far. So lastly, some very quick points. I'm not going to read all these out. These are common sense. You'll be able to read the slides when and if you choose to do so later. These are just common sense basic principles that I would suggest anybody follows when and if they're pursuing significant retrofit work. If you're just having your loft done, you might not want as many quotations as I'm suggesting, or as many people to talk to, but I would work towards these for any project that you're undertaking. So some headline guidance. So key takeaways, just to help everybody remember: every pre-1990 home will need to be substantially retrofitted by 2050. It's yours and mine included. Net zero can't be achieved by simply buying green energy. You can't, it's not like buying indulgences. You've got to actually do the work. And you've got to think about integrating retrofit with other planned works. Use a fabric first whole house approach. No insulation without ventilation. And that's pretty much the end of my talk. Lastly, for those who are interested in the other end of the shovel, and this is me wearing my kind of academic or university hat, some of you may well be interested in this. We have a talk in 2 days' time at City University where I work, where we've got the world-renowned John Elkington and Jessica Seymour, who have recently been involved, and particularly Jessica, been involved in the Klimasenjorinnen case, which was a case where the Swiss, a collective of about 2,500 older people in Switzerland took the Swiss government to court at the European Court of Human Rights, holding them responsible for acting in a way that is commensurate with their ability and their families and their grandchildren's abilities to live in a safe planet. And essentially that's been going through the courts for the last 2 years. It's a landmark case, and it's going to be discussed by this lady who was prosecuting essentially representing the Klimasenjorinnen against the Swiss government. And John Elkington's world-famous, renowned speaker and on corporate ESG, and he'll be talking about whether there is responsibility for corporates in this space or whether that sits with government. So it'll be an interesting debate and one that you may be interested to. It's an open public lecture, so feel free to come if it interests you. So thank you very much. That's me.
Thank you very much, Dermot. Fantastic talk. And I just want to give a little personal appreciation that I heard your guidelines about getting the steps to go through to get a heat pump about 4 or 5 years ago, and I followed them, and we've got a heat pump, and it's all going well. So thank you. I'd like to turn now to Stewart Mcilroy, our final speaker. Stewart's house has been one of the mainstays of the Green Open Homes programme for a very long time, don't know how long, but I remember going round it several years ago, one of the first ones that I went round, and I think it's been inspirational for a lot of people over many years. And having been a management consultant, he's now made a transition into running his own company, where he's brought some of the skills that he developed on his own house into a business which is the underfloor insulation company.
Thank you.
Stand up behind the lectern.
Oh, okay. I thought I'd go and look like a builder, at least.
Can you stand behind the lectern?
Yeah.
That's right. Otherwise you won't be on camera.
Is it right button?
Let me just get your slides up.
So I'm going to talk about... Yeah.
You can't wander, you have to stay there.
Yeah, so I'm going to talk about energy efficient refurb of an Edwardian house. 3 things. I won't be too long, I hope. Basically talking about what we did, an overview of the house and what we did. Then the results of what we did. Yeah. And then talking about more of an agile approach to doing stuff. As I've said at the bottom there, knowing what to do and having the money is not enough. You've actually got to do things. If we go to the next slide. So, as Jeremy said, I've had a variable career. So I talk about on-site stuff, 10 years on construction sites around the world, like cold countries, hot countries, building stuff. Not houses, other stuff. And then 10 years of office stuff. That's like writing reports, strategies, like really useful stuff, as you can imagine. And then the really useful stuff is the builder stuff at the bottom, where you actually do practical stuff, where you can see a real result from the work you do during the day to a benefit to a real human being. Underfloor insulation. Then if we move on from that, this is our house at the end of the street. what we bought, a bit of data on that. Yes, you could actually buy a 3-storey, 5-bedroom house for 237,000 back in 1997. I should have said earlier that I actually went to the University of Salford. But probably I went there before David was born. Anyway, so getting back to the house. So typical house, as Dermot said, pre-1900, end of terrace, solid wall, sash windows, suspended timber floor, very cold. That was the house we got. We bought it, it was old, dirty, drafty, cold. What did we do? Looking back, this is what we did in 3 phases. I think, like most people buy an old house, the first thing they do is they go in and, I've got to knock that wall down, I'm going to do an attic conversion here, I'm going to extend the kitchen, and I'm going to have underfloor heating and put a little island thing in there. And no, we didn't do the island thing and extend the kitchen, but we did stuff because you go in and do stuff like throw out the carpets and then you find you're really cold. So it was doing a bit of that. And then we got into doing the energy efficiency stuff, which was, draught-proofing. We changed the boiler to a more efficient gas boiler, and then we did the various insulation things. But this was more about observation and looking at, I'm cold. What should I do about that? Go on the internet, find something and do it. I remember the getting into solid wall insulation was the result of being on holiday in Sweden and visiting a replica of a Swedish peasant's house of 1850. Timber house, and you could go in and you could touch the wall and it wasn't cold. And then you come back and you touch your Edwardian house wall and it's cold. So you think, I should do something about that. So I went on the internet, and I've got to admit, I don't have the insulation. I'm the one on the far right, by the way, the far right in your slide. But I haven't pulled it up to see what's going on underneath. I've put wood burners in, which would I do today? Possibly, probably not. And then we went into put secondary glazing on all the windows, a cheaper version, got a picture later of it, and then we got into the other stuff like solar PV, fill your roof with solar panels, solar hot water, air source heat pump, blah, 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 all that techie stuff, we've done all of that. Would I do all that if I did it again? No. Would I do it in the same order if I did it again? No. But we learned. So after the retrofit, we managed to retain, or I would say enhance, the period features of the house. So it basically doesn't look like, it still looks like an Edwardian house. So there's the visuals on it, which is very important when you've got to bring your wife with you to do this sort of thing. I think one of the most effective things we did on the house was put in an internal porch. Or you could argue putting back an internal porch. In no cold country do you ever go directly into somebody's house. There's a door you open, you take your shoes off, you shut the door. Then you open the other door. The British houses, you go straight into the house. Or you stand at the door gossiping. And I remember when we moved into my house, my wife would always, if a friend was leaving, she'd stand at the front door, just chat to them, with the door wide open. And you think, now she at least has a porch. Underfloor insulation, what is it? We use sheep's wool, it's breathable, between the joists, under the floor. And also take advantage of the storage space under the floor. It's a greatly underused resource in most Edwardian Victorian houses where you could actually put stuff there. That's where we keep our wine. Secondary glazing, we have this Magna Glaze system, which is perspex, magnetic, you stick to the window frames. So it's a low-cost, effective option. Again, something I've found on the internet, just by Googling secondary glazing. Solid wall insulation, this is the very thin stuff. As I said, it's the one on the right-hand side in Dermot's slide. Have I got mould under the insulation? I've got to say I don't know. I've no evidence of it. I haven't pulled up the insulation to have a look. I could cut a bit out. Maybe I should, just to see. But I see it where we are. It's a bit like you stick a plaster on a wound and then you pull it back to see if your wound is healing or not. Or you've glued something, you think, oh, I wonder if that stuck properly. Pull it up, yeah, it had actually stuck properly, yeah. So I may do it, I may not. But I see no evidence of any damp. It would be interesting with University of Salford if they wanted to do maybe a site visit and do some free investigation on my house. I have all the data for 20 years of energy use on the house. You can look at the features, put sensors up, and it's free of charge. So there's an offer for you. We also did all the stuff that Dermot's talked about, heat pump, solar hot water, the solar PV, I say 2 tranches. We did the feed-in tariffs, which Dermot fitted, which have worked really, really well. And then new solar panels, which you don't get them to report in one app now because you can't get feed-in tariff for new panels. You only get them for the panels you put in at the time. Solar hot water, you could argue, was a bit going down a blind alley because once we put the heat pump in, you get lost in this, I need to integrate this with that. So you integrate your heat pump with your solar hot water on the roof, which means you've got to run all these pipes and stuff in your house. Material cost, labour cost, it would have been cheaper at that point to throw out the solar hot water and put more photovoltaics on the roof. So we have made a few mistakes along the way. And we've recently added a battery and an electric car charging point for my new Citroen e-Berlingo, which I was just changing my car insurance today, and I found my car insurance was actually £200 cheaper because I had another driver on my insurance policy. Dermot Barnes, so you saved me £200. Anyway, approximate costs of what we did. I think it says 70,000, 68,000. That's all the work on the house over 15, 20 years to do that. But the key thing on that is excludes my time. You know, if you added my time, especially at my outrageous charge out rate, yeah, you would increase that figure significantly, probably double it, if not more. And the results of what we did, so 2 graphs, one is gas, the top one's gas, the bottom one's electricity. So the y-axis is kilowatt hours use per day, average on a rolling 360 day over a year. So the gas one starts at 40. So when I started collecting the data, we were using 40 kilowatt hours per day of gas on average. We're now using no gas, so we've come off gas completely. We decommissioned the gas range hob this year. But even before that, we were down at like 1 or something like that. You can see the bottom graph goes up. That's the air source heat pump, where the electricity goes up. It's starting to come down because you start to use the heat pump more economically. But it's still gone up. And that you can see it going down on the electricity graph from putting in solar panels. And you can also, if you look at it, you can see the impact of COVID on both graphs, from working from home. And the other results from Dermot says it's more comfortable. It's more comfortable, good for the planet. Lower energy bills, that's OPEX, and happiness is a good thing. Or how you quantify happiness, I don't know. But we didn't have a plan. There was no plan for what we did on the house. We just did stuff. What we did was driven by what we knew at the time and how we lived in the house, what made sense, and also, I've got to say, what money we had available, and what I was willing to do. We had children, and my wife worked as a childminder when we had the house, so obviously you've got to have the rooms done for the children that you look after. So you focus on different things because of what is required, and you spend the money you've got. Did the absence of a whole house plan make any difference? Yes, I would say it would. I would not have put probably internal wall insulation as I have. There's other things I wouldn't have done. But I would say you could tip that on its head and say that, yeah, but I actually did stuff that I probably wouldn't have done if I'd done a big plan. And the work is ongoing in a house. And as they say, I think in the Greece they say, when the work is finished, the house dies. So there's ongoing work to be in the house. So it's good to have ongoing projects to improve. For example, when I did the underfloor insulation in my house, on my own house, I put 100 mil of insulation under the floor because the joists were 100 mil. As an installer, I now fit 200 millimetres under other people's floors. So I've now gone back under my floor to add another 100 millimetres of insulation by crawling under my floor in a space about that much. And yeah, it's a bit mad, I know, but yeah, I get a lot of fulfillment out of it. So when we talk about agile, this is the point I really want to make about is being agile. What is agile? And does anybody here work in software design? So you'll know what agile is. See, agile basically comes from software design, where some software developers in the US, they got together because generally software used to be designed in the way that you'd ask all the users what they wanted the software to do, and then you'd capture all that information in what is something called a requirements definition document. We've got it in this document. You'd sign that off. That's what we're going to build. You'd go away and build it, you'd come back to the users and present it to them. And it generally was not what they wanted. They'd say, yeah, I like that bit, can we have more of that? I'd like to have got more of that, but I don't really need that. Oh, and have you done this? So you don't get what you want by doing that, defining everything up front, what you need. So they moved to agile, which comes from, agile embraces change. You do things, it may work, it may not work, but if you're going to fail, you could argue you're not failing, fail small. You know, as Einstein said, or is it Einstein, one of those guys said, somebody asked him, how did it feel by trying out 100 things and they all didn't work? And his answer was, I found the things that didn't work to be able to find the thing that did work. Something like that. It was not failure. So being agile is do a bit, review. If it works, you can do more of it. If it doesn't work, try something else. That's what I think. And that's how I think I've done the house refurbishment. I've done it in an agile way. And lessons learnt about from what we've done. Draught-proofing is key, I think, from that. I would have done that as number one. And what I've thought also is the term compartmentalisation in terms of, and I see this when I go to see houses and doing underfloor insulation, where you look at it and you think, I can do this underfloor insulation for your house. You're still going to be cold after I've done this because there's a gap there under your front door. You're still not going to have anywhere in your house that you could go to and be warm on a really cold day. So why not start by thinking, let's find somewhere in your house that you can do something and you know you will be warm there, whatever happens. That should be number one of people, what people should do. And you don't need to do 100% everywhere. Again, I see this from doing underfloor insulation. The customer they'll have front reception room, which they don't use because it's too cold. Generally, always they have no insulation. Or they'll say, do you think the radiator's too small? The radiator doesn't get warm. Do I need a bigger radiator? And you think, no, you need to insulate under your floor. And then you talk about this, and then it goes to, yeah, but should I do the hall as well, or should I do my kitchen? And it's what you call scope creep. It then goes from being 18 square metres to it's now 35 square metres. So they've doubled the scope of work. It now becomes a number which they don't have or are not willing to spend, and the work doesn't happen. Whereas they could just go and do the front reception and be warm and do the other stuff later. You don't need to do it at the same time. It shouldn't be a reason to avoid doing things because you can't do it everywhere. Also, the point there, you can't be perfect because you're not perfect. And also, I want it cheap and I don't want any disruption for the work. I'm not going to do it. You're not. That doesn't exist. You're not going to get that. It shouldn't be a reason to avoid doing stuff. And the final one as well is, and I would say this, is take advantage of opportunities. There are opportunities to do work. I find this as a supplier in that the customer really wants you to fit in and with their schedule. But in all honesty, they should be jumping at when you can do the work. You know, if you're, as a supplier, you're booked up. If you have 3 days, the customer should grasp that, rather than think, yes, I want all of that. I want it to be perfect, cheap, non-disruptive, and I want you to do it next week. That is not an option. Thank you.
Thank you very much, Stewart. Yeah, I mean, maybe if you sat over there with Dermot, we're very short of time. If I think we said we were going to finish at 9, but maybe we could just have a couple of questions. What I'll do is I'll bring the mic round if anybody's got a question, which can be for any or all of our speakers.
Hi, thanks very much. All very interesting. Thank you all very much. My question was mostly for Dermot, but anyone. You talked a lot about the no insulation without ventilation. I was wondering if there's any sort of fairly easy way to see how healthy your house is on the inside. So you talked about comfort and health within the home as well, without getting in a sort of expensive external someone to check it all out. Can you get like humidity monitors, or how might you be able to look at that yourself? Thanks.
Yes, you can get humidistats, very simple ones and very inexpensive ones, and they range from something that just is like an indicator you stick on the wall and it'll tell you almost like a temperature is, but it'll give you percentage humidity, and you'll be able to understand whether you're over or under your humidity by understanding what the norms are for the space. The normally is a calculation that you can do very straightforwardly by just multiplying the length by the breadth by the height of the room to get the cubic volume, and then you'll understand whether you're within a limit or outside the limit. You can also get slightly more sophisticated versions of those where it'll download to an app on your phone or on a computer. So those would be indeed very sensible ways of doing it. Much more basically still, understanding condensation in the space. If you are getting condensation on the inside or even on the outside of windows, that's a different issue. But if you're getting condensation on the inside, that will be a good indicator of the fact that you have a problem and that moisture is not getting out of the building as it should be getting out of the building.
Thanks for all the talks. Just a quick question to Dermot. With the PASS registration process, who actually carries out the inspections during the work and on completion to make sure it's being done properly?
So the PASS process involves those three people that I mentioned. There's a retrofit designer, coordinator, and it is normally the coordinator who has responsibility for making sure that the work has been carried out the way it should have been done. So somebody starts by assessing the building, somebody does the design work, and then somebody coordinates the work is carried out and signed off in accordance with the design.
So I have a question with regards to the agile approach, which I like, and again also to the retrofit sort of overall plan. If I think of insulation of a roof, where I have different components, like a pitched roof part, then one is a bit more accessible, some of it is not accessible, and then I've got a flat roof. So can I go and say, okay, the flat roof is the easy win, I'm doing that first. The bit which is sort of accessible if I have someone like Stewart, I do next. But then there is one bit which is really a challenge because I need to take the roof tiles off and it's a big deal. Now, is there a risk now if I don't do it all at once that I get these kind of thermal bridges and I end up with huge problems of condensation and mold? Or can I say, okay, if I use, let's say, breathable materials, then I can do it like that. It's not ideal, but it's a bit more comfortable than before.
I think I'll pass that to Dermot.
I would be very, very cautious about doing work to the roof area in any building in a piecemeal way. It needs to be joined up. Doesn't mean it can't be done in stages. It just means that it needs to be completely considered and assessed and planned and executed. And one of the areas of buildings where you get faults developing the most radically or the most obviously is the roof, and the other, of course, is the below the footings in a building. So I would be very, very careful about doing piecemeal work in a roof, and you need to look at it on an individual project by individual circumstances will dictate. Yeah.
Hi, another question for Dermot. So we've been told, yeah, let's insulate either internal or external, let's avoid drafts, let's ventilate. What type of ventilation would you recommend apart from trickle vents? Are we talking about mechanical or some other passive ventilation?
So the amount of the ventilation strategy will be dictated by how much air changes you need to deliver. So it's actually a fairly scientific and actually very basic formula. You'll have X number of air changes you need in a space per hour per day, and you can therefore calculate whether that can be done passively, as in through just things like air bricks and things like the trickle vents that are in a window or a door. I would advocate against doing that, because that is introducing additional elements of uncontrolled ventilation. So if you spend, I don't know, £1,000 on an expensive door or window, and then you drill a hole in it to allow air to come in, you've kind of destroyed a large percentage of the value of the £1,000. So in that case, what you need is some sort of an automated extract vent, which is electrically powered, but it will be consuming very small amounts of energy, super small amounts of energy, and it will automatically do the number of air changes you need. Now, you can buy these kinds of extract fans for 100, 200, 300 quid, depending on how big they are and how automatic they are, and whether they recover heat with the air. So in other words, they will change the external and the internal air and retain the heat. So you could and probably should be doing it in a controlled ventilation way, using some sort of active ventilation, but it does depend upon the space in question.
I just wanted to put in a quick question for David, that you mentioned about problems with air source heat pumps not being installed properly. We had an earlier talk which was mentioning gas boilers not being installed properly or not being set properly, and that there are a lot of condensing boilers that were running too hot to do any condensing. Do you have any any observations about that?
I think lots of things go wrong when the installer gets involved. If you, to be honest, gas boilers. The thing is, what you want to do is the water needs to be coming back really from all the radiators below 54 degrees for your boiler to be running most effectively, most efficiently. So certain things you can do really is try to make sure your system's balanced. That's quite tricky, but that's trying to make sure the radiators all heat up at the same time, at the same rate. If you can reduce your flow temperature, when I was talking about that flow temperature reduction thing that you can do, actually throughout a year, you actually, if your boiler's not changing its flow temperature of the water for the radiators, depending on the external temperature, quite often you can change that periodically throughout the year. So in effect, you could maybe when you put your heating on in September, October, you could maybe set your flow temperature down to lower than 60, maybe even as low as 50 or even lower than that degrees centigrade. That's going to effectively mean that the water anyway is going to be coming back at that temperature, which is meaning your boiler is going to be running most efficiently. So you can get away with those low flow temperatures with your gas boiler for a lot of the year, and then gradually increase it as you get into midwinter, and then reverse that process again throughout the rest of the year. So you don't really want to be seeing lots of condensation coming out of your flue, lots of flue gases coming out of the boiler when you see it out of the flue. So I'd aim to try and get that flow temperature down, so you're not seeing lots of big plumes of exhaust flue from your boiler. Get that flow temperature down, and hopefully that should result in a lower return temperature and more effective boiler operation. And that's something anyone can do quite easily.
So my question is about roofs. So we've heard about there's a lot of heat loss through roofs, and also about planning your retrofitting around things you might be doing to your house anyway. So can you achieve the same reduction in heat loss through having a loft conversion as you can simply through insulating your pitched roof?
I don't know.
The short answer to that question is no. And the reason is a very basic scientific principle basis. If you are introducing a loft conversion, you're introducing additional area through which heat will be lost. So, you know, if you imagine you have a typical kind of twin pitch roof, and then you introduce a kind of half a cube or whatever as an extension to create that, you are then fundamentally changing the way heat will be lost through that space by introducing additional surfaces through which that heat will be lost. And of course, you're going to be more than likely introducing a heat source to an area that didn't have a heat source before, as in the loft space becomes habitable, whereas previously it wasn't habitable. So, you know, you're changing the functionality, the space and heat demand, as well as the building physics by doing what you've described. It doesn't mean that you can't make your dormer extension thermally efficient. One thing I would also just suggest while you mention it is if you're creating a loft, one of the biggest issues with lofts these days is that they overheat in summer quite a lot. And that's because they use typically a foam-based petrochemical insulant, which allows heat transfer into the building very, very quickly. So, you know, typically lofts are uninhabitable in summer. I mean, that's an exaggeration, but for certain periods of the time. And if you measure the temperatures, they are often in loft conversions beyond accepted norms and recommended temperatures, both during the day and the evening. So the way to get around that is to use natural insulants, which reduce the speed at which heat is admitted into the building, as well as reducing heat loss. So that's one approach that you can take. So yeah.
In our house we have a loft. We did a loft and we segregate the loft from the rest of the house as a door. So you basically use the loft during the day and then close it off when you're not using it. So it's another option. You could treat it like that. And in all honesty, if you need the space, as I say, I'm more practical. You need the space. There's the space.
I think we probably, can I just say that we have two more very quick questions. I'll just...
Thank you. The thing is, I've been to several of these meetings and I feel sceptical. I always feel very sceptical about the proportion of people that attend as to their understanding of the basic physics. And I feel so strongly about this that I almost feel that it would be worthwhile, this is really directed at you, sir, the Director of Sustainability, that it almost ought to be a program built into the school curriculum at secondary school or primary school level, with a very hands-on sort of approach. For example, a mock enclosure, 3 foot square, for example, with a mouse living in it, completely insulated for permeability, so hands-on children could begin to see the effects, and it could just develop from there. And you know, when I come to these meetings, I always feel that everyone is at a disadvantage because they don't really grasp the fundamental physics. So there we are. Thank you.
Thanks very much. I think it's a very valid point, and yeah, if we had the 1 hour that it takes to give a 20-minute lecture, we could be doing that here. But I agree with you that it would be also good if people were educated at the school level and at the university level about these things, so they had a better understanding of the thermodynamics, you know, of heat loss and so forth.
Just one final question. If you have in your home one or more rooms that you don't use regularly, then from an energy and cost perspective, it feels sensible to not heat those in the winter months when you're not using them. However, can that cause problems in terms of mold growth or any other issues if you have a room that's cold for a long amount of time? And what is the best thing to do about that? Do you actually need to heat it all the time, or can you heat it once a week to a certain temperature to stop mold growth, or how would you deal with that? Thanks.
So the answer to that question is it's going to depend on the room, and right down to which direction it faces, how much sun it gets, or not, and what's going on in that room. If there's nothing going on in that room and there's no sources of moisture being created in the space, then there shouldn't be too many problems associated with condensation or mold growth. But if other parts of the house are transmitting moisture-laden air into that space for some reason, or you're drying clothes, or there's a bathroom next door, or whatever, then that can cause an issue. As a sort of very basic rule of thumb, I would have ideally temperature zones in the house where you're heating according to your usage of the space. So you wouldn't just heat the whole house in one way at one temperature for one period of time, or one heating cycle. So you would, as a rule of thumb, perhaps you would introduce some heat into that room for short periods of time, but it does depend upon what the room usage is and how much moisture it receives and heat it receives from outside, etc. But yeah, you certainly don't need to heat it all the time, if that would be crazy.
Do you use a dehumidifier? Use a dehumidifier. We close the doors of all the rooms we don't use, turn the thermostat right down, never had a problem.
Okay, I think we've run a little bit over time, but I think we need to come to an end. And I would like to first of all thank the three speakers very much indeed for really excellent, a huge amount of knowledge that's been communicated in a really accessible, interesting way. So a round of applause, please, for our three. And the other thing to say is this is the end point of the Green Open Homes Programme 2025, so you're going to have to wait with bated breath another whole year for a repeat. But I would like to thank David Coombs, who's done a fantastic job of being the technical wizard for all three talks, so thank you very much. The other person who really deserves a lot of thanks is our administrator, Lisa, who has been the central person. And also, they're not all here, but all the hosts of homes who've put on the Green Open Homes tours. It's not a minor thing to invite a load of strangers into your home, and a lot of people have been willing to do that, and it's much appreciated. And thank all of you for coming, and all of you live stream, or if you're watching it on YouTube, thank you very much for taking the time.